It's a great pleasure to talk about our recent work in Europe, and the title is towards reviewing the mystery behind chain of thought, a theoretical perspective. This is a joint work with my amazing collaborators, and here I will talk about this paper, and this is my outline. First, I will talk about the basic background such as the chain of thought and the autoregressive transformers, and will discuss the topics in this talk. Then I will present a basic preliminary, such as the autoregressive transformer, and then I will present our main result, showing that chain of thought is the key to solving mathematical problems and even many general problems. And finally, I will give some experimental results. And okay, let's start. So large language models have demonstrated many emergent capabilities in various aspects, such as the generation, question answering, and mathematics, and coding and reasoning. And the last three types of questions are considered challenging since it involves complex reasoning. But empirical results have shown that large language models can do very well on these challenging tasks. Currently, most large language models follow the so-called autoregressive paradigms. The autoregressive paradigm means that it treats various tasks uniformly as a sequence generation problem. Here we can show an example. The task is translate English to French, and then we will give some examples, and finally end with the task we want to translate, the word cheese. And the transformer takes all this information as input and then output the translated French word. And all this procedure is performed in an autoregressive way. So we call the transformer autoregressive transformer. And we also call the input the prompt. And the answer is generated by predicting subsequent tokens conditioned on the prompt. And in this talk, we will focus on the chain of thought prompting, which is a very promising technique proposed in the last year. Here, chain of thought mainly focus on the reasoning problems. For example, consider a simple mathematical task where the task need to calculate some basic arithmetic. If we directly let the large language model to output the answer, it will generate a wrong answer. And you can see in this figure. But if we add a prompt by adding the phrases, let's think step by step, then the model can generate a correct answer, although it also generates other information such as the intermediate steps. And also chain of thought prompting has been used in other settings, such as the in-context learning. If we give some in-context examples to a transformer model, where the in-context example uses the chain of thought, then the autoregressive transformer can generate a chain of thought and output a correct answer. So after the development of chain of thought, many promising questions emerges. For example, there are several central questions. The first is, how can we theoretically understand the power of COT generation? And this is the key question studied in this talk. But also there are other questions, such as how can prompt trigger the COT, or how can COT emerge in large language models trained over massive data? These questions may relate to the generalization or the optimization of large language models, and we will not focus on these topics. So in this paper, we will focus on the first aspects by answering two central questions. The first one is, are there inherent limitations of large language models in directly solving math reasoning tasks without COT? And the second one is, what is the essential reason behind the success of COT in boosting the performance of large language models? Okay, so we will enter the second part. We first give a brief introduction of the autoregressive transformers, which is very familiar to us. And here, in a transformer, the input is a sequence of tokens. And the initial embedding in a transformer consists of two parts. The first part is the token embedding, namely using an embedding layer to generate a d-dimensional vector. And also, the second part is the positional embedding. It is used to distinguish different positions. And we simply add both embeddings to obtain the initial embedding before the transformer layer. Okay, so then there are several transformer blocks, and each block transforms the input using this equation. Here, each transformer block consists of two parts. The first part is a multi-head self-attention layer, and the second part is a feed-forward network. Here, the attention head we use the standard formulation, namely the self-max attention. And here the FFN is a two-layer network. And we also use the standard GLU activation, which is used in many prior works such as the GPT. And for autoregressive transformers, in the softmax attention, there is a mask. The mask is causal so that each position can only attend to the preceding positions. After L transformer blocks, the last entry of the final layer will be used to predict the next token. And then we concatenate the predicted token to the end of the input sequence. And we can repeat the above process. This can iteratively generate subsequent tokens. And we end the procedure until the end of sequence token is generated. This is the introduction of autoregressive transformers. Okay, so let's continue to the third part. We'll show that chain of thought is the key to solving mathematical problems. It is well known that transformer-based large language models have exhibited surprising mathematical capabilities in various aspects. For example, some mathematicians have shown that large language models can aid the development of new theorems. It is very surprising. So can we gain insights into their power in these mathematical tasks? We consider two basic tasks. The first one is arithmetic, and the second one is equation. Both tasks are very elementary and serve as building blocks in solving complex real-world mathematical problems. We will consider two setups. The first is to directly generate the answer, and the second one is to generate a complete COT solution. Here are some examples. We will use the standard GPT-4 to demonstrate how COT can improve the performance of mathematical tasks. Here we will use two prompts. The first prompt is direct. It will let the GPT to directly generate the answer. And the second one is the chain. It means that generating intermediate steps. Okay, we first let GPT to solve the arithmetic task. We can find that it output a wrong answer when using the direct. But if we let the GPT to generate intermediate steps, it can precisely output a correct answer. But it also output many long intermediate steps. And if we consider the linear equation, the situation is also the same. Directly answering the linear equation is impossible. But if the transformer generates intermediate steps, it can arrive at a correct answer. Okay, so next we will formally describe how to define the two problems. Here we consider a very standard COT format. In the arithmetic expression, we can calculate each operator in one step. For example, here in the first step, we simply compute the 7 plus 5, and the other tokens are just copied. And we can continue this process until generating the correct answer. And for the linear equation task, the COT format is also very standard. We just use the Gaussian elimination. Namely, we can eliminate one variable in each step. And then for a linear equation containing n variables, we will use n steps to eliminate these variables and obtain a final answer. And this is the definition of chain of thought format. And also, we will consider a simplified setting. Here, we consider that all numbers in the sequence are in a bounded range between 0 and p minus 1, where p is a prime number. We consider this setting because the standard setting involves floating point numbers. Even we only consider integers as input, the presence of division will also generate floating point numbers. And so it's very hard to unify the floating point numbers as well as the operators to a unified format. So here we consider the integers of a bounded range. So all the integers and the operators can be uniformly treated as tokens in a predefined vocabulary. Okay, so we can define two tasks. The first is arithmetic NP. It means that we will evaluate arithmetic expressions on the input of length bounded by n, and the computation is under the finite field mode P. And for the equation task, we similarly consider equation MP. It means that we consider the linear equation with no more than m variables, and also the computation is performed in the finite field mode P. And before presenting our central result, we also need a concept called log precision transformer. It is a practical setting where in a transformer, all internal neurons can only store floating point numbers within a finite log n bit precision. Here, n is the maximal length of the input sequence. First, this setting is very practical because in practice, the sequence length is typically much longer than the machine precision. Commonly, we use the 16 or 32 bits machine precision, but the sequence length can reach thousands or even millions. And another reason of using the log precision is that it is a necessary condition. If we want to store the positional embedding, then the number of values in the positional embedding is already polynomial in the input length. So we at least need log precision. And also, log precision implies that the number of values each neuron can take is polynomial in the input length, which is also a reasonable condition. So we are ready to present our first main result. This result shows that standard autoregressive transformers without COT cannot solve both mathematical problems. Here, specifically, it means that if we want a transformer to solve a mathematical problems without COT, the required hidden dimension must grow superpolynomially in the input length. So if the input length is slightly longer, the required transformer size will grow prohibitively large, and thus it cannot solve both problems. So how can we prove this result? Our proof is based on a key insight called the circuit complexity. Actually, we use a prior result which shows that the transformer can be characterized by a computation model or a circuit. This is because all the basic computations in transformers, such as the addition, multiplication, or nonlinear activations, or the softmax, can all be represented using a circuit, and thus its computational power will be bounded by the circuit complexity. Here, a well-known result states that a pure transformer is bounded by the complexity of TC0. So it's very actually very weak. It corresponds to a shallow circuit. TC0 means that the circuit can use basic gates such as AND gate, OR gate, NOT gate, and also the threshold gate, where the threshold gate means that it takes a Boolean vector and output 1 if the number of 1 is greater than the number of 0, and output 0 if the number of 1 is less than the number of 0. And this is the definition of threshold gate. And so we have shown that the transformer is limited in the expressive power. But on the other hand, we prove that for the both mathematical problems considered in this paper, the computational complexity is lower bounded by another complexity class called the NC1. It is a standard complexity class. It means that we can use the AND gate, OR gate, and NOT gate with a fan-in of 2. It's a standard AND gate and OR gate. And we can use a depth of a log depth with respect to the input size. So the depth now is not constant. This contrasts to the TC0. And also for all these complexity class, we can only use polynomially a polynomial number of gates. We prove that for the considered mathematical problems, such as arithmetic and equation, they both are lower bounded by NC1. We use the reduction from NC1 complete problems. Specifically, we show that the arithmetic task is harder than the Boolean formula evaluation problem because the AND OR can be implemented by addition or multiplication. But the Boolean formula evaluation is already harder. It's already hard enough and cannot be implemented using the TC0. And for the equation task, we show that it is harder than the automaton membership testing. This is a standard problem means that we will check whether an automaton can accept a given string. This is also a NC1 hard problem. So the takeaway is that the transformer is limited in the expressive power when directly generating the answer. And the reason is due to their limited parallel complexity. Okay, so we next turn to the case of using COT generation. It turns out that now we have positive results. We show that a constant depth transformer model can already solve both tasks. Here we use a transformer of depth 5 and using 5 heads and a constant hidden dimension independent of the problem size. And moreover, we show that all parameter values in the transformer are also polynomially bounded by the input size. This is our main results. And so how can we prove this result? Actually, our proof is based on construction. We first construct a series of basic operations that can be achieved using the attention head. We show one attention head can perform two types of operations. The first is conditional copy, and the second is conditional reduction. Here, conditional copy means that the transformer will copy the embedding in the previous token, satisfying certain conditions. For example, the transformer can copy the latest number in the previous sequence, namely generate a number that is the nearest to the current position. And this is an example of conditional copy. And conditional reduction is similar. If we consider average, the transformer can average the information of several previous positions, satisfying certain conditions. For example, it can take sum of all numbers in the previous sequence. And this is an example of conditional reduction. And so we first show that attention head can perform the two basic operations. Then we show that the MLP can perform computation. It can perform many types of computations, such as linear transformation, multiplication, and the most important one is the conditional selection. Here, conditional selection is a logic operation, and it will serve as a basic building block to form a complex algorithm. And so, for a complete transformer model, we will stack multiple layers of attention and MLP. This corresponds to read from previous position and then make computations. This can form a complex algorithm, since attention head can be seen as reading from previous memory, and the MLP can be seen as performing computation. And combining them will be able to compose a complex algorithm. And we show that the arithmetic task and also the linear equation task can be characterized using parallel algorithms, and this algorithm can be implemented by a transformer. And finally, we can make some discussions. First, we show that in our proof, we use a polynomial upper bound for the parameter values. And this guarantees that the constructed transformers can be implemented using log precision. And the second is, in our COT, we consider a very practical setting. where the COT is written in a readable math language format. This is very practical and may give evidence that the large language models have the potential to convey meaningful human thoughts through grammatically precise sentences. And finally, we can discuss how can large language models equipped with COT bypass the impossibility result. This can be understood via the effective depth of the transformer circuit. When employing COT, a major difference is that the output will be looped back to the input, and such a loop will create dependency between different output tokens. And this will lead to a significantly deeper circuit with depth proportional to the length of the COT solution. And in this way, the expressive power of transformers can go far beyond TC0. And this is the insight of COT generation. Okay, so next we will switch to the more general problems. Here in the previous section, we consider the mathematical problems, but we know that the large language models is quite powerful in many tasks besides the mathematics. So here we turn to a general setting. We will show that COT can implement a very powerful reasoning framework called the dynamic programming. Here, dynamic programming is a very well-known framework that breaks down complex problems into a series of small subproblems, and so that each subproblem can be tackled easily by combining the answer of previous subproblems. And then we can solve all these subproblems in a sequential manner, and finally obtain the desired result. This is the idea of dynamic programming. There are several key concepts in dynamic programming. First is the state space. Here, the state space characterizes the subproblems in a dynamic programming process. And also, there is a partial ordering between different states, so that we will solve different subproblems according to the order. And second is the transition function. And each state will depend on several previous states, and the dependence will be characterized using a transition function. Here we consider a restricted setting as presented in the formula. Namely, each state will depend on a finite number of previous states and also a finite number of input tokens. But we will show that this setting is already very general and will include many examples we will show later. And finally, the aggregation function. When we finish the dynamic programming process, the final answer can be obtained by combining all the DP answers. For example, here, the aggregation function can be summation or taking max or mean. Here are some representative examples of dynamic programming. All these examples fit in our framework. For example, the longest increasing subsequence or the added distance. And we will not specifically describe them, but they are representative examples of dynamic programming. So our result is to prove that autoregressive transformers can generate the DP reasoning chain. We consider the following format. First, there are several input sequences. We consider n inputs and separated by a special token, for example, this one. And after the input, the transformer will generate all the DP states and answers in a sequential manner. And finally, it will generate the answer. And this is a natural reasoning chain of dynamic programming. So we prove that the transformer model of a constant size can solve dynamic programming for all inputs. And here also the parameter of the transformer is polynomially bounded by the input size. And the proof is also similar to previous one. We use the construction, and also we show that we can use the softmax attention to fetch the related inputs, and then use MLP to compute the transition function, and finally output the DP answer. And also we have impossibility result, which shows that if we do not use COT, then the transformer cannot generally solve dynamic programming problems. An example is the context-free grammar membership testing. This is a celebrated dynamic programming problem. And we show that it is intrinsically hard to be solved directly without COT. And also, this problem is actually a P-complete problem. So this implies that when equipped with COT, the transformer can be quite powerful. It can solve some P-complete problems. Okay, so we'll finally present some experimental results. Here we consider all the tasks in our theoretical analysis. We consider the following 4 tasks: the arithmetic expression, linear equation, and 2 types of dynamic programming problems. Here in all these tasks, we can see that using the COT can always achieve a perfect accuracy. But if we do not use COT, generally the performance is poor. Here we can take the arithmetic expression task as an example. In this task, we consider 3 levels of difficulty. Namely, we consider a sequence of 4 operators, 5 operators, and 6 operators. When we use when the sequence consists of 6 operators, it can be seen that the performance is very poor. Even using a 5-layer transformer, the performance can only be 50%. It's very poor. And also for the linear equation, we can see that without COT, the model achieves nearly 0 performance. So this shows that COT is crucial to boost the performance of large language models. And also here in our experiments, we train the transformer from scratch using the generated COT data sets. So this implies that the model can easily learn COT solutions given sufficient training demonstrations. And finally, we also consider the length extrapolation task. We consider training a transformer model using small sequence, but tested on longer sequences. Here, in the arithmetic expression task, we train the model with all sequences less than 15 operators, but test them using a number of operators. The number of operators can be 18. But in this case, the generalization is still good. Here, the problem is that when the sequence length is longer, the learnable positional embedding may be problematic since it is not appeared in the training data sets. So this is the main reason why the performance drops, but it's still fairly high. when considering longer sequences. So we can make conclusions that COT can indeed generate to longer sequences. Okay, so this is the main result of our paper, and there are also several promising directions for future work. But here, for some questions, it may be hard to analyze theoretically, but we also list them. Some of these questions also present in the original work of COT. Mainly, it is still challenging to consider the generalization or data or optimization of training large language models when the COT is presented. And also, in our experiments, we show that it performs very well empirically, even in length extrapolation tasks. But currently, a theoretical explanation is lacking. And finally, our result in this paper can also lead to some interesting questions of how to design in better architectures to solve complex problems in an efficient manner. For example, we show that standard transformers with COT are very powerful, but recently there are many variants of transformers. For example, there are sparse transformers, and also there are many other positional encodings. And these transformer variants may change the expressive power and may result in some drawbacks. So we think another interesting question is how to maintain the expressive power of transformers while using a more efficient design, such as using sparsity or other promising architectural improvements. And this is my today's talk, and thank you for listening.